Hi, this is Jordan Xiang from UIUC. Here I'm happy to present you our paper, Good Case Latency of Byzantine Broadcast in PODC. This is joint work with Itai, Kartik, and Lin. As we know, state machine replication is a crucial part in permission blockchain. And the motivation and the main question we want to ask and answer in our paper is how fast can state machine replication be? In reality, most of the SMR solutions are leader-based, meaning there is a replica that acts as a leader and try to propose its value or block and try to make everyone else agree on its proposal, even if some of the nodes are malicious. So if the leader is honest and make progress, we call this a steady state. So during the steady state, the honest nodes will make progress agree on the ever-growing ledger. Otherwise, if the leader is bad, or maybe the network is bad, then all the nodes will trigger a view change protocol and try to replace the leader with the next one. And again, if the leader is honest and the network is good, then all the nodes will back to the steady state and make progress. Since the steady state is a period when the protocol makes progress, and the view change is triggered less frequently, so most of the SMR solutions are designed in such a way that they try to make steady state more efficient than the view change. In other words, they try to optimize the good case performance where the leader is honest and the network is also good, so that all the honest nodes are staying steady state and making progress. And this is exactly the question we want to ask and answer in this paper. That is, what's the fundamental limitation of the latency performance under the good case? So in this paper, we'll study both broadcast and SMR. So the broadcast is a single shot problem where a sender tries to make everyone agree on a single value. And we study broadcast because it's a cleaner theoretical abstraction, and also we can derive like latency efficient SMR protocols from a broadcast. And similar to SMR, the good case of broadcast is when the sender is honest. One thing to note is that our good case only requires the sender or the leader to be honest. So this is different from some previous works, which adds a fast pass to the protocol under the best case, which asks all the nodes to be honest. So our good case requirement is much weaker than the best case requirement. And the good case latency definition is just the latency under the good case, meaning the time since the leader or the sender proposes its value to the time when all the honest nodes commit their value. Here we summarize our results for good case latency. First, we derive type bounds for authenticated BFT broadcast protocols. Here, authenticated meaning the broadcast will use signatures. So we consider all three popular timing models, synchrony, partial synchrony, and asynchrony. So in different timing models, we'll derive type bounds with respect to the different resilience threshold. And also from these broadcast protocols, we are able to derive faster BFT SMR protocols. And these protocols improve the previous state of the art, including sync hot stuff and fast BFT. Let's start with the results under Synchrony, which is also the most interesting case. So under Synchrony, the problem we look at is a standard Byzantine broadcast. So here we distinguish two different message delay bound. One is the assumed synchrony bound, big delta, which is the worst case delay bound over all possible executions. Another one is the actual bound, small delta, and you can think that as a actual latency bound for some particular execution. So therefore, this small delta bound is unknown to the nodes or the protocol designer. And for the clock synchronization, we also distinguish two different models. One is the synchronized start. So here we are in a perfect world when all the nodes can start the protocol and their clock at exactly the same time. And in contrast, we can also assume unasynchronous start, where the clock at each replica or nodes has a clock skew at most small delta. So there are several clock synchronization protocols can ensure that. Here we summarize our good case latency lower and upper bounds under different resilience. So as you can see, as the resilience increases from 1 up to n-1, the lower and upper bound for good case latency will also increase. The number of Byzantine parties is less than 1/3. We can see the tight bounds is too small delta. Recall that the small delta is the actual message delay bound. So that means under Synchrony, we have protocols that can commit in 2 rounds and tolerating 1/3 corruptions. So moving forward, when the number of corruptions reaches exactly 1/3, the tight bounds becomes 1 big delta plus 1 small delta. So here our results implies any broadcast protocol that tolerates 1/3 or more than 1/3 corruptions will have to lose responsiveness, meaning the protocol cannot progress in the actual network speed because there is a lower bound, 1 big delta says you have to commit after 1 big delta plus 1 small delta. Then further increasing the resilience to be between 1/3 and 1/2, then we reach the most interesting case where the tight bound results actually depend on our clock assumptions. So recall we can assume the clock are synchronized so that all the nodes have synchronized start. In this case, the tight bounds is the same as the 1/3 case, which is 1 big delta plus 1 small delta. However, in the more practical case where the clock at different nodes are unsynchronized, and in that case, we can show the tight bound becomes 1 big delta plus 1.5 small delta. So this case is in particular interesting because the tight bounds is not a multiple integer of the message delay. Our 1 plus 1.5 bound is tight, but our construction is quite theoretical. So for the practical side, we also have a synchronous SMR protocol that can achieve near optimal latency, 1 big delta plus 2 small delta. So this protocol improves the previous best sync hot stuff, which has latency 2 big delta plus 1 small delta. So we almost improve the latency by a factor of 2. We actually have an interesting journey from the 2 plus 1 in sync hot stuff to 1 plus 2 in this new practical synchronous SMR, and finally reaches the 1 plus 1.5 of the optimal good case latency. So we summarize the intuition of our journey in this post. So anyone who's interested can check this out. So the last row is the dishonest majority case, where we have a lower bound, and the upper bound can be derived from a recent paper. And as you can see, there is still a gap of factor of 2 in the between the lower and the upper bounds, and that's the only case that is not tight in our paper, and this problem is still open. Now let's move to the partial synchronous case, where the network delay is unbounded before GST and becomes bounded after GST. Under partial synchrony, there are no standard broadcast formulations. Since we want to capture state machine replications like PBFT, here we propose a new definition called PSync-BB. So PSync-BB is similar to Byzantine broadcast, but has several differences, and we mark the difference in red. So first of all, it also has agreements, ask all the nodes, all honest nodes to commit the same value. It also has validity, which asks if the sender is honest and the network is synchronous, then all the honest should commit the sender's value. Also, it has termination, which asks all the honest to commit after GST. So if we think about it, and it exactly captures the case like PBFT, where if the leader is honest and the network is synchronous, then all the nodes will commit the leader's value, and after GST, all the nodes will commit the value and make progress. So the PSync-BB actually solves a single shot of SMR. So this table summarizes our tight bounds for PSync-BB under different resilience. So as you can see, there is a clear boundary of equal to 5F minus 1 that separates the tight bound of 2 rounds and 3 rounds. So for the 2 rounds, the lower bound is kind of trivial, and we propose a new protocol for PSync-BB that achieves 2 rounds. And for the 3 round, the protocol is just PBFT, and we in fact prove that if n is less than 5F minus 1, then 3 rounds is the best you can do. Our 2 rounds PSync protocol can be thought as a 2-round PBFT protocol, because by definition, our PSync-BB solves single shot SMR. So also our resilience is 5F minus 1. So in the special case when there are only 1 fault, we only need 4 nodes to achieve 2 rounds. In contrast, the previous best approach, FAB, it will need 5F plus 1 nodes, which means it will need 6 nodes when there are 1 fault. Also, in this special case, our resilience is the same as the original 3-round PBFT. The second bullet is that we refute the optimality claim of FAB that saying 5F plus 1 is a boundary separating 2 rounds and 3 rounds. We show that actually 5F minus 1 is the right boundary. And a concurrent work in PODC this year also obtains a similar result. They also show that 5F minus 1 is the right boundary, and they also propose a 2-round PBFT protocol and show a lower bound of 3 rounds if n is less than 5F minus 1. Now we will briefly explain the intuition of how we improve upon PBFT and FAB. So recall that PBFT is a 3 rounds protocol with in n equals 3F plus 1. So the 3 rounds consist of 1 round of proposing and 2 rounds of voting. The safety of PBFT basically relies on the current intersection. Within a view, there cannot be two different sets of 12+1 votes voting for different values, since their intersection will contain at least one on its node. And cross views, the current intersection of 2f+1 nodes that lock on V once a value is committed, and the set of 12+1 timeout messages will contain also at least one on its node. So this on its node will include V in its timeouts and enforce the next leader to repropose the value V if V is committed. Now let's look at Fab, which is a two-round protocol with 5f+1 nodes. So the two rounds includes one round of proposing and only one round of voting. So here the safety within a view is similar to PBFT, since now we have even larger cordon size. So there can't be two sets of different votes within a view. They're voting for different values. So within a view, only one possible value can be committed. But for the safety across views, it's a bit more tricky, since here we only have one round of voting, and we can only rely on the current intersection of the set of nodes that voted for the value and the set of nodes that send the timeouts across views. So for instance, if a value V is committed, there must be 4f+1 nodes that have voted for that value. And so in the intersection, there will be at least 3f+1 nodes that have voted value, including 2f+1 on its node. Since 2f+1 is a majority of 4f+1, to help our understanding, let's consider what happens if we reduce the number of nodes by 1. So if there are only 5f nodes, and we look at this current intersection again, then the intersection will contain only 3f nodes, which means there are only 2f nodes that have voted for V and include V in their timeout. Since 2f is exactly the half of 4f timeout messages, and the other half of the timeout messages could include other value V prime. So the new leader, there is no way for any node on its node or the new leader to distinguish which value is the actual value that's actually being committed. So in this case, the safety cannot be guaranteed. Here comes our new observation. So if this situation happens and the timeout messages contains two different values, since the values are signed by the leader, that proves the leader is actually bad. Actually, we can use this observation to reduce the resilience from 5f+1 to 5f-1. So again, consider this intersection. Now, in the current intersection, there are only 3f-1 nodes, and there are two cases. If the timeout messages only contain one value signed by the leader, then there is no confusion. The new leader can just repropose this value V. However, if the timeout messages contain two different values signed by the leader, then we know that this previous leader is bad, since it equivocates. In this case, all the on its node can just wait for one more timeout messages from anyone other than the leader. This ensures the timeout messages will only contain f-1 bad nodes. Then if any value V is committed, we can show that the timeout messages will contain at least 2f messages that includes V, so that it is a majority of the timeout messages, and the new leader can repropose V to ensure consistency. Furthermore, we show that the resilience is optimal for two-round PSync BB. And the concurrent paper in PODC also shows this is optimal for two-round consensus. Finally, we have the asynchronous case where the message delays are always unbounded. Here, the standard broadcast formulation is reliable broadcast, which is weaker than the standard Byzantine broadcast, since Byzantine broadcast cannot tolerate a single fault under synchrony. Here, for reliable broadcast, we show the time bound of good case latency is always 2 rounds. So the lower bound is kind of trivial, and our protocol construction is also simple, but it is something new. To conclude, our paper presents a complete categorization for Byzantine fault-tolerant broadcast. We show time bounds for broadcast under asynchrony, partial synchrony, and synchrony. So these results answers our previous question on what's the fundamental limit of the latency performance of state machine replication on the good case. So our broadcast constructions can also derive faster state machine replication protocols. For example, under partial synchrony and synchrony, we obtain faster SMR protocols compared to the state of the art. So this is the end of the presentation, and thanks for watching.